Welcome to Module 14, Transport Layer. After Module 13's ICMP troubleshooting tools, this module goes back up the stack to Layer 4, TCP and UDP. This is a long, detailed module covering both protocols headers, TCP's connection process, and reliability/flow control mechanics. Objective: compare transport layer protocols supporting end-to-end communication. Preview the long topic list on screen: data transportation basics, TCP overview, UDP overview, port numbers, the TCP communication process, reliability/flow control, and UDP communication. This module builds toward a full picture of how TCP and UDP each handle delivery differently. The transport layer handles logical communication between applications on different hosts, establishing temporary sessions and reliably delivering data. Think of it as the bridge. Application layer above needs data delivered, and the transport layer is what actually links that need to the lower layers doing the real network transmission. 4 core responsibilities shown on screen: tracking conversations, keeping tabs on individual sessions, segmenting data, breaking it into pieces and reassembling at the destination, identifying applications via port numbers, and conversation multiplexing, handling multiple simultaneous conversations at once. Every one of these gets its own deeper coverage later in the module. IP only handles structure, addressing, and routing. It never specifies how delivery actually happens. That's the transport layer's job, and it's exactly why TCP/IP provides 2 different transport protocols instead of 1. Different applications have wildly different reliability needs. The on-screen line sums it up well. IP delivers the packet. The transport layer decides how carefully. TCP is reliable and full-featured, guarantees data arrival at the cost of extra processing. Use the registered letter analogy. You sign for it, so the sender knows for certain it arrived. 4 core functions shown on screen: number and track, acknowledge, retransmit, and sequence. TCP must establish a connection before any data flows. That's why it's called connection-oriented. UDP is the simpler alternative. No reliability, no flow control, fewer header fields, faster processing. Use the regular mail analogy. Drop it in the mailbox and hope for the best, nobody's tracking it. 2 defining traits shown on screen: connectionless, no session setup, data just gets sent, and stateless, neither side tracks the conversation, also called best effort delivery. Choosing the right protocol depends on the application's tolerance for loss versus delay. VoIP and live video favor UDP. They can tolerate some data loss but not the delay retransmission would cause. Databases, banking, and email require TCP, since missing data could corrupt the whole transaction. Walk the 2-column comparison on screen for concrete application examples. Beyond basic segmentation, TCP provides 4 core services shown in the table: establishes a session, negotiates before any traffic flows, ensures reliable delivery, guarantees every segment arrives, provides same-order delivery, sequences segments so they reassemble correctly, and supports flow control, can ask the sender to slow down. Mention RFC 793 as the full spec for anyone who wants the deep details. TCP is stateful. It tracks exactly what's been sent and acknowledged from session start to finish. A TCP segment adds 20 bytes of overhead. Walk the header layout on screen row by row: source, destination port, sequence number, acknowledgment number, then header length, /reserved, control bits window, then checksum/urgent, then optional options field. Field by field walkthrough of the TCP header shown in the table: source, destination port, 16 bits each, identify the applications. Sequence number, 32 bits for reassembly. Acknowledgement number, 32 bits, next expected byte. Header length, reserved. Control bits, the SYN, HCCUF, IN flags. Window size, checksum, and urgent. This table is worth having students copy down for reference. TCP's layer design means applications never have to handle segmentation, reliability, flow control, or reordering themselves. They just hand their data stream to TCP and trust it to take care of everything. Walk the application examples on screen: HTTP, HTTPS, FTP, SMTP, Telnet, all relying on the same underlying TCP layer beneath them. UDP is simplest described by what it doesn't do compared to TCP. 4 gaps shown on screen: order as received, no reordering, reconstructed in arrival order, no resending, lost segments are just gone, no session, no establishment step at all, and no feedback, sender never told about resource availability. UDP is stateless, neither side tracks the session, and its header reflects that simplicity: just 4 fields totaling 8 bytes, a fraction of TCP's 20. Walk the header layout on screen: source port, destination port, length, checksum. UDP's data unit is called a datagram, sent purely best effort with 0 guarantees. Field by field walkthrough of the UDP header shown in the table: source port and destination port, 16 bits each, identify the applications, length, the datagram's length, and checksum, error checking. 4 simple fields compared to TCP's 9. This simplicity is exactly what makes UDP so much faster to process. 3 application types that suit UDP best, shown on screen. Live video/multimedia, tolerates loss, not delay. VoIP, streaming, simple request and reply. Small transactions where a reply may or may not matter. DNS, DHCP, and applications that handle their own reliability. SNMP, TFTP. The app manages retransmission itself if needed, not the transport layer. Both TCP and UDP use port numbers to juggle multiple simultaneous conversations. Every header carries a source port, originating app, and destination port, requested service. A host requesting a web page dynamically generates a unique source port per request, so multiple conversations can run at once, while the destination port, like 80, tells the server exactly what service is being requested. A socket combines an IP address and a port number, source IP plus port, or destination IP plus port. Walk the example on screen. One PC talking to the same server for both FTP, source port 1305, des port 21, and web, source port 1099, des port 80, simultaneously. 2 completely separate sockets between the same 2 devices, kept distinct purely by port numbers. IANA manages the full 16-bit port space, 0-65535, split into 3 groups, shown in the table. Well-known ports, 0-1023, reserved for common services like web and email. Registered ports, 1024 to 49151, IANA, assigned to specific requesting applications. And private dynamic ports, 49152 to 65535, also called ephemeral, assigned by the client OS per conversation. Reference table of well-known ports worth having students memorize or keep handy. FTP, 2021, SSH, 22, Telnet, 23, SMTP, 25, DNS, 53, DHCP 6768, TFTP 69, HTTP 80, POP3 110, IMAP 143, SNMP 161, HTTPS 443. Point out DNS uses UDP for client requests, but always TCP for server-to-server communication, one of the few apps that uses both protocols. Netstat lists every active connection on a host, protocol, local/foreign address and port, and connection state. Genuinely useful for spotting unexplained or suspicious connections, a real security concern. Walk the sample output on screen. Point out netstat-n shows raw numeric addresses/ports instead of resolved domain names and application names, useful when you want the unfiltered view. Every server application process uses a port number, either auto-assigned or manually configured. Critical rule. A server can't run 2 services on the same port within the same transport protocol at once. No double booking TCP port 80. An actively bound port is considered open, and a server can have many ports open simultaneously, 1 per active service. The 3-way handshake establishes a TCP connection before any real data moves. Use the human handshake analogy for the mutual greeting concept. 3 steps shown on screen. SYN, client proposes a session and initial sequence number. SCN, server acknowledges and proposes its own reverse session. ACK, client acknowledges back. Connection now fully established. Concrete walkthrough with actual sequence/ACK numbers. Step 1. A sends SEQ equals 100. SYN. Let's start. My ISN is 100. Step 2. B replies SEQ equals 300. ACK equals 101. SYNAC. Got it. My ISN is 300. Expecting byte 101 next. Step 3. A replies SEQ equals 101. ACK equals 301. ACK. Got it. Expecting byte 301. Ready to go. Note real ISNs are randomized, not round numbers like this example, specifically to prevent certain attacks. Closing a TCP connection sets the FIN flag. Since TCP is full duplex, really 2 independent one-way sessions bundled together, each direction needs its own FIN ACK handshake, meaning 4 total exchanges to fully close one conversation. Either side can initiate termination, not just the original client. Step-by-step termination example on screen. Step 1. A sends FIN. I'm done sending. Step 2. B sends ACK. Got it. Step 3. B sends its own FIN. I'm done too. Step 4. A sends ACK. Got it. Session closed. Note, the client/server labels are just for clarity. Any 2 hosts with an open session can initiate this. TCP is full duplex, meaning every connection is really 2 independent one-way sessions, with control bits tracking exact progress throughout. The 3-way handshake accomplishes 3 things at once, shown on screen. Confirms presence, the destination is actually there. verifies the service, an active service is accepting requests on that port, and announces intent, informs the destination a session is being opened. Since segments can arrive out of order or not at all, TCP assigns a sequence number to every segment, representing that segment's first data byte. During setup, both sides agree on an initial sequence number, ISN. As data flows, the sequence number increments by the byte count transmitted. Real ISNs are randomized specifically to prevent certain attacks. This course uses simple numbers purely for clarity. Classic TCP acknowledgment has a real limitation. It only confirms the next expected byte, not which later segments already arrived. Walk the example on screen. Segments 3 and 4 are lost, so host B can only say ACK 3 feet, send starting from segment 3, forcing host A to resend segments 3 through 10, even though 5 to 10 already arrived successfully. That waste is exactly what the next slide's SAC mechanism solves. SAC, selective acknowledgement, fixes the wasteful full resend problem, negotiated during the three-way handshake if both sides support it. Same scenario as before, but now host B can reply ACK3 SAC 5 to 10, explicitly confirming it already has 5 through 10 and only needs 3 and 4 resent. Host A resends just those 2 segments instead of 8, dramatically less wasted bandwidth and congestion. Flow control governs how much data the destination can reliably receive, managed via the 16-bit window size field. Walk the numeric example on screen with window size 10,000 and MSS 1460. Each segment send advances the sequence number, and each ACK confirms receipt while reopening the send window for more data, keeping the pipe full without overwhelming the receiver. MSS is the largest amount of data, excluding the TCP header, a device can receive in one segment, negotiated during the handshake. Walk the calculation on screen. Ethernet MTU 1500 bytes, minus 20 byte IPv4 header, minus 20 byte TCP header, equals 1460 bytes MSS, explaining exactly where that 1460 number from the previous slide's example came from. Congestion causes overloaded routers to drop packets, and unacknowledged segments are how the source detects this is happening. Left unmanaged, retransmissions can actually make congestion worse by adding more traffic to an already overloaded path. When TCP suspects congestion, the source reduces how many bytes it sends before waiting for an ACK. Important that it's the source adjusting itself, not the destination's window size changing. UDP is ideal for time-sensitive traffic like VoIP, precisely because it skips connection setup entirely. A small header, zero network management overhead, data just goes. Contrast this visually with the 3-arrow TCP handshake from earlier in the module. UDP is just a single arrow, no setup steps at all. Like TCP segments, UDP datagrams can take different paths and arrive out of order, but UDP has no sequence numbers, so it has no way to reorder them. UDP just reassembles data in whatever order it arrives and hands it straight to the application. If correct ordering actually matters, it's entirely on the application itself to sort that out. UDP won't help. Just like TCP, UDP server applications get assigned well-known or registered port numbers. When a datagram arrives at one of these ports, UDP simply forwards the data to the matching application. No extra session tracking or validation involved, keeping the process fast and lightweight. UDP client-server communication starts the same way as TCP. The client requests data from a server process. The client dynamically picks a source port for the conversation. The destination port is usually the server's well-known port. That same port pair gets reused, reversed, for every reply in the transaction, without any session state tracking it. Close the module walking each bullet. The transport layer's role linking application to network. TCP's stateful/connection-oriented, reliable nature with its 20-byte header and three-way handshake. UDP's stateless, connectionless, best effort simplicity with its 8-byte header. The 3-port number ranges and what a socket is. The 4-way FIN ACK closing process. SACK's efficiency improvement over classic ACK. And flow control via window size, MSS, and source-side congestion throttling.